Okay, so optimizing optimizations. Okay, so I'm Hiromi Ishii from JijModeling. So I'm so honored to be here. So, okay, so here's today's topic. So first we skim through overview of our product JijModeling and the problem of constraint detection, and see some performance measurements, and then introduce some heuristic lessons learned from our implementation. Okay. So let's start with overview. JijModeling is a mathematical optimization modular provided as a Python EDSL implemented in Rust. And for those who are not familiar with mathematical optimization, modular is a tool to describe the and encode optimization problems as some sort of mathematical versions. And the solver solves them exactly or approximately encoded problems exactly or approximately. And this is used in production or company on daily basis. And here is the example program that encodes traveling salesman problem and quadratic formulation. So you can see it is it seems some kind very resembles the mathematical model presented here. Okay, so enough for advertisement. So let's dive into the motivation that related to EGRAPHS'. So constraint detection problem. So the point is that there are specific types of constraints which can be exploited to solve problems efficiently. So there are so-called one-hot constraint or unit simplex, or special ordered set of type 1 or 2, etc., etc. And the previous example of TSP indeed involved so-called two-way one-hot constraint. So, so note the interchanged subscript here. So these two constraints jointly constitute a two-way one-hot constraint. And solvers provide dedicated APIs for specifying such constraint explicitly to gain the solution time. But the problem is that if one is expertise in mathematical optimization, they can find they can spot such good constraints by hand. But many practitioners need not be it is not necessarily be aware that such constraints they are writing such good ones. So here's the so-called constraint detection problem. We coined that term. All right. So modelers should detect such constraints from even unaware user input. So to call dedicated API automatically in place of users. So here are two challenges in constraint detection problems we solved here. So one is to avoid combinatorial explosion. So detection time must not depend on input size. And here NA is not the number of equation, but actual input size. So array or so in the TSP example, N is the number of CT or so yes. So it must depend only on number of equation, but not actual real-world data size. So if we detect the above two-way one-hot naively, one must match against n times in the formula, and so if there is one matching this one, then try everything else to find this pattern. So this will lead to the combinatorial explosion when done naively. And the second challenge is we have to take algebraic congruences into account. So there can be several ways of expressing the same constraint. So for example, so these three formulae are all equivalent, and so we must detect each terms as equally equally. So how JijModeling solves these problems? So the point for the first point, the combinatorial explosion, JijModeling separates symbolic representation from input data. So instead of expanding summations or four-old constraints, it stores them as is symbolically. Well, it might sound rather trivial to programming language people, but in the industry of mathematical optimization, vast majority of modelers treats formula and input data in mixture, and the task of constraint detection problem almost infeasible. So we are just buying into using ASTs. So and then two-way one-hot constraints from the previous slide is just two formulae. So we can just find two formula is yeah. Okay, so the second point is algebraic congruence, and as you might guess, we employ EGG to compute congruence closure here. So, and one possible alternative is to define some normal form and compute them and compare them. But we didn't take this route because the term language is somewhat complex. Okay, so let's see. Let's skim through our complexity of the term language. So the term language of JijModeling consists of two layers. So one is expression language. So it contains arithmetic operations and reduction operators or aggregations. So here, not this. Yeah. So this particularly involves bound variables and arithmetic and etc. etc. Okay. So and we are working on version 2 with arbitrary lambda abstraction. And constraint and it contains constraint terms. So comparison of two expressions to be used as a constraint of mathematical optimization problems. So we don't think any feasible complete normal form can be defined for it. So we decided to use EGRAPHS. Okay. So it's the overview. So first, see the performance measurements. So, okay. So, as an example, we are interested here in so-called special ordered set of type 1. So, briefly, this demands a list of non-negative variables. So, exactly at most one of non-negative variables to be non-zero. And the important point is that if the data is mixed with expressions directly, this term will become n many formulae. So we must use symbolic representation to just pattern match against 2 instead of m times n plus 1, yeah. And the particular problem we are trying to formulate is the two-plant placing problem. So briefly, we are to place plant in each east and west region to minimize some cost. So detail doesn't matter, but the point is here two SOS1 constraints, and these are encoded in this style of using big M-like notation to encode it as a equation. Okay. So we formulated this in JijModeling 1.12.3 and using PySkipOps solver as the solver, and compares without detection version and with detection version in terms of runtime. Okay. So the first, let's see the runtime in without detection. So if we don't exploit the information in SOS1, the runtime seems exponentially grow. It shows exponential growth. On the other hand, if we detect SOS1 automatically, it is very constant or linear, it seems. So asymptotic improvements can be achieved. So even if input size is only 60 or so, this difference is evident. So in practice, our constraint detection problem, solving constraint detection problem really buys something to us. So with timer, it usually takes approximately 1 second for constraint detection. So and in practice, solving problems takes much more time. So this overhead is almost negligible in your adaptation. And we haven't measured the saturation rate yet because completeness of detection with respect to algebraic growth is not so important in practice because we can already cover some variation and equations that can arise naturally, I think. So we think it works well. So okay, so it gives us indeed great speed ups in solving problems. So let's go to the case study part of constraint detection, implementing constraint detection in terms of EGRAPHS'. Okay, so we will talk about architecture of our constraint detection with EGG in JijModeling, and heuristic for writing rewrites learned through the course of implementation. So here are some rules. And finally, we introduce some utility Rust library built on top of EGG library. Okay, so our constraint detection proceeds as follows. So it first converts each constraint into a separate EGRAPH. So separation is not essential, but for simplicity reason. So it allows identifying original constraint without IDs, issuing IDs. So we can just match against each EGRAPHs and avoid bound variable collision here. And saturate with realized and analysis. And the analysis part consists of two parts, typing and constant folding. Why we need typing here will be covered soon. Okay. And then apply patterns to each EGRAPH for detection. Okay. And currently we are manually checking conditionals for composite detection, such as SOS1 for general variables. Okay. And here some excerpted rewrite rules. So it consists of rules for constraint terms. So equality or inequality rules. And some algebraic rows involving reduction operators, and that lattice rows, Boolean operations, and for Boolean and order applications. And we will cover why we come up with these rules from now on. So first heuristic to choose these rules is bidirectionalized rules. So there are some bidirectional rules in the previous slides, and this is because we perform pattern match externally after the saturation. So suppose we are to detect term, so in the left associated form of ternary sum, and further suppose saturated EGRAPH contains right associated variant. Then if the associative row is only unidirectional, the saturated graph does not include the form of these refs associated ones. Hence, the matching against this pattern will fail. So listen, so always bidirectionalize rules for completeness when, at least when you perform matching after the saturation. Okay. So the heuristic 2, it's a use type information for soundness. Okay. So there are some rules guarded by side conditions on types, such as A to A plus 0 if A is real or float. And this seems the opposite direction of A plus 0 to A. So why not just bidirectionalize it according to the previous rule? Well, this is because opposite rule can reduce type information. So if A plus 0 is well typed, then we can infer that, well, by our definition of language, A must be float number, but not vice versa. So if we have a conditional rules instead, it leads to ill-typed writing such as true to true plus 0, which doesn't make sense at all. And such a rate might seem harmless at the first glance, but in our experience, indeed such rules once made all floating numbers equal. For some reason, we couldn't make out the exact reason, but it does happen. Yeah, and adding such side conditions, such behavior disappeared. So this is why the reason why we are currently having typing in our analysis phase. So lesson. So when treat multi-typed language, use type information to ensure soundness. Yeah, this is very crucial. And here's 6.3, the prefer reductive rules of analysis. So there are some rules that follows from other rules on constant forwardings. So for example, a plus minus a to 0 can be derived from other rules and constant forwarding as follows. It might seem adding overhead to the saturation, but in our experience, adding reductive rules like this dramatically improves the saturation time. And we didn't have time, so we couldn't add the benchmark result here. But for some terms, in our experience, it took approximately 5 seconds to reach the fixed point and without the rule, but only less than 1 second after adding such reduction rules. So lesson, do not rely on constant foldings. Adding reductive rules can improve saturation time. Okay. And the saturation here means saturation or timer, but for small terms, it indeed reaches to saturation. Okay. And here, and these are the heuristics, and okay, only 3 minutes left. So we will skim through egg recursive in brief. So we during the course of development, we also developed the egg recursive built on top of egg. So this allows us to use egg without S expressions. So some egg expression-based API has some downsides. We think so. Relying on from string and display or S expressions are parsed at runtime, not compile time. So even if the given expression has syntax error, users cannot notice. And complex expressions are just hard to parse by humans. And the hard to comprehend the meaning of positional argument expressions, and egg recursive aims to solve these pains. And for example, this is the typical example of egg rewrite rules, and this becomes this. So everything was coded in string, but now it is written as genuine last program. So here we use times and plus operators here, and I bet you're not aware this closing parenthesis is redundant or extra, and it will lead to runtime error, but we are not aware. So if we use S expression based interface, we are not aware this extra closing parenthesis. So, but if there is such thing, Rust compiler will warn us. Okay, it seems that we are running out of time. So we can derive such, okay. So, and we can just large arguments can be guarded with view types that provides named arguments, okay? And we can derive such definitions and smart constructions with macros, okay? Okay, so future work and conclusion. So there are much space for future work. So we are considering using egg log instead of egg. So it should remove the current manual conditionals and the bindings. So detection of SOS1 on general variables involves the first detect the SOS1 on binaries and then general non-negatives. So such conditionals can be expressed naturally in egg log, we think. And apply solidity graphs to treat bound variables properly. So I will attend the talk tomorrow. Yeah. Okay. And also use eGraphs to solve typing constraints on a tensor shape in our version 2 of JijModeling. So we have dedicated type system in upcoming version 2, so we can use eGraphs only also in typing, we think. And we are planning to remove typing analysis phase in favor of proper type system. Yeah. And consider combining eGraphs with partial normalization and constraint detection. So store constraint only form of E1 is less than or equal to 0 and normalize it. So this is a suggestion from reviewer A. Thanks. Okay, here are conclusions. JijModeling is, to our knowledge, the first versatile mathematical optimization modeler supporting constraint detection mechanism. So it detects specific constraints that and tells solvers to exploit such information. This will improve the solution time dramatically, and eGraphs play a crucial role in such mechanism in JijModeling. And we skim through some lessons, and we also introduce some egg recursive grade. Okay, and part of this work is performed for Council of Science in Japan. Okay, here are references, and thank you.
Thanks so much for that great talk. I think we have time for one quick question while we change over speakers. So if the next speaker could just go ahead and get set up. Do we have any questions from the audience? I've got a quick question. In terms, one thing that you didn't mention is the role of extraction. I know that that's a problematic area for a lot of these eGraph applications. Did a sort of straightforward approach work for you, or did you have to do something more complex?
Yeah, we didn't. We just matched against eGraph, but not extraction, because we want to preserve the user input, the form of user input. Yeah, but indeed, there must be space for exploration to optimize the expression of mathematical optimization. So that must be interesting point. Yeah, thank you for the suggestion.
Okay, sounds good. Well, let's thank the speaker again, and
thanks.
get set up.